And so to the last of our finalists. They're from the Canon Slade Grammar School in Bolton, and they've been measuring the force of attraction between any two bodies, a force known as Big G, gravity.
It's gravity which keeps the planets in orbit, and it's the same force which keeps us firmly rooted to the ground.
11 stones. It takes the entire mass of the Earth, millions and millions of tons, to attract me with a force of only 154 pounds.
What we hope to measure is the force of attraction between these small lead spheres and the large steel cylinders.
It's taken the boys a year to design, build and test the apparatus to measure this minute force of attraction. A thick steel case rests between two massive steel cylinders. Inside the case are the lead spheres and a small fixed mirror suspended from the top of the apparatus on a fine wire. The rod and weights twist slowly back and forth, attracted to the large steel cylinders by the gravitational force.
In order to measure the strength of this force, we need to measure the period of oscillation of the beam. That is the time taken for it to twist back and forth once. The trouble is that the force is so small that this takes about an hour. In fact, you can hardly see it move at all. So we had to devise a system whereby we could monitor the movements of the beam.
Light from a laser is directed through a system of lenses and mirrors to the inside of the steel case. Here, it's reflected from the small fixed mirror at the centre of the glass rod. As the rod and weights move, a moving spot of light is reflected from the mirror onto a meter rule.
We could stop up all night to record the movements of the spot, but that would be tiring. So we've designed a camera which will record the movement of the spot on film.
And Margaret Weston, the first question is yours once again.
Stephen, why is Big G important?
Well, it has a importance in cosmology, determining masses of black holes, and also in solar theory, sort of determining the mass of the sun.
Has Big G been measured as accurately as, say, the velocity of light?
No, that's one reason why we decided to do it, because it's only known to about 0.1%, whereas things like the speed of light are known to, many places of decimals.
What's the difficulty? Is it just small?
It is very small, and it's very difficult to measure.
Where do you think, Richard, the main errors are going to occur in the end?
Eventually, the main error will come from lack of stability in the filament, and the periods will not be exactly the same each time, which is something that you can't do anything about. It's a limit of the method.
Yes.
Who last measured Big G accurately?
Hale was the last person to measure it accurately, back in 1942.
And he did it in very different circumstances to the ones you have, didn't he?
Yes, he was, had a lot of money, for one thing, and a lot of time. But we've got some advantage over him. We've got a laser, where he was just using a projector. And we've also got a computer, which saves a lot of work. Yeah. But then again, Hale didn't actually do the work, he had some sort of subcontracted it.
Given all this money and time that Hale had, do you think somebody could measure it much more accurately now? Have there been any developments which help this sort of measurement?
I think it could be possible, yes, much more accurately. There's an experiment by the National Physics Laboratory.
Well, what would you do? I give you all the money and time you want. What would you do? Make a more accurate measurement than Hale?
Well, you've got money, you can make more accurate spheres, bigger cases. You can...
The principal modification would be to use Radnicek's method. Yeah.
Which
instead
is?
Of Hale's
You'll have to
method.
explain that.
What is that?
Which is, instead of having the large masses fixed, to suspend those from a torsion balance over the top of the smaller torsion balance from a wire about, say, 10 metres long, and then to adjust the period of this large torsion balance to correspond to that of the small torsion balance until you set up a system of resonance. And then you're measuring, it's like measuring a beat frequency.
That's the resonance method you
yes.
referred to in your
yes.
account, I see.
And this,
do you think that's better, do you?
It gives you a far more accurate determination of the relative periods. Because, as I say, you're measuring a beat frequency instead of just the ordinary frequency.
Yes.
Which could, it's never been done accurately. So Radnicek did it in about 1930.
Why didn't you do that?
Well, because of the sheer physical problem of suspending the large masses, but we're thinking seriously of doing that at the moment.
Where will you undertake that particular experiment?
Well, at the present we're under the stage, and on the stage above, we have about 10 metres of height. So if we could drill a hole through the stage and send the wire through there, then we could gain a 10-metre suspension.
And do you reckon that it's vibration-free enough in your area?
Well, we don't know.
Can you explain to me why you embarked on such a precision measurement?
Because it's not been done frequently and it's not been done accurately, like the speed of light.
How much of a challenge has it been?
It's been a very big challenge. Yes.
And would you do you make any claim at all, Stephen, about having got a number at all within any sort of accuracy?
We've got a rough measurement using a stopwatch and a ruler of 6.1, which is 10% down. It's 10% out, but I mean that's quite close.
It's an improvement on what you did before, which was how much was that out?
That was 1,000 times out, but then we weren't expecting to get any good results.
No.
How much longer will it take you to get a really good measurement?
It's hard to say.
Yes. It must be.
So there we have the final finalists, as it were, from Cannon Slade Grammar School in Bolton. And so now we come to the time when we find out who are the young scientists of the year 1978. And to give us the assessment of all the judges and also to present the Royal Institution Trophy, it's the man who's been with this programme right from the word go, right from when it started, Sir George Porter. Sir George.
Well, taking the teams in the order in which we saw them, first the Royal Grammar School, Newcastle. This team took two well-known ideas, the hovercraft and the low-volume sprayer, and had the idea of putting them together to produce something new and useful. What's more, after an enormous amount of effort, they have got a prototype to the stage where it can be used and tested in the field. So they needed both originality and hard work, imagination and perspiration, and they used a lot of both. Second, Malvern. This project appealed to us because the team used one basic equipment for three different geophysical techniques. They therefore learned the principles and something about the electronics involved. It all started as an assessment of a piece of prototype equipment, and they've certainly given it a thorough testing. They've been able to show how newer techniques can improve on results from older, more subjective methods. Well, now third, Kenton School, Newcastle, with their studies of sulphur dioxide pollution. This was a wide-ranging piece of work involving chemical analysis of air and fuels, studies of growth patterns on lichens, and an extensive statistical analysis of the effects of wind and weather on sulphur dioxide levels. We were impressed by their painstaking treatment of the results and the care they took not to jump to easy conclusions about cause and effect. Well, lastly, Bolton. This is the sort of precision measurement not normally even contemplated in a school. The team haven't yet overcome the experimental problems, and this doesn't surprise any of us. But they have shown great determination in attacking those problems, and their mathematical skill is impressive. With more time, we hope that they will be able to produce really reliable results. Well, the judges found it extremely difficult to distinguish between three of the teams, and we've decided, therefore, this year to announce only the winner. We have, in this case, unanimously decided that in the first place, the young scientists for the year 1978 are the team from the Royal Grammar School, Newcastle.
Very good. Congratulations. Very well done. And so, with the Royal Grammar School Newcastle receiving the trophy and the title Young Scientist of the Year, it's goodbye until next year.